Then we will go on with our very last presentation for today. Daniel Winter from the Fraunhofer Institute for Solar Energy Systems is presenting today the results, or probably some results, of the ReWaCEM project. As I said before, ReWaCEM, well, it's an abbreviation of recovery of acids and metals from pickling solutions of the metal processing industry. And as I said before, they were together with Inspire Water and SpotView in the Spire call, Water Management in Process Industry. So I'm really curious about what you have to present today, Daniel.
Hello and welcome everyone. I hope you can hear me.
Yes, we can.
Okay, great. So I will going to start with the presentation, or let's say a small look into the project ReWaCEM, which we have done with a lot of project partners during the last 3.5 years, and we ended the project in 2019. I will just give a short introduction into the basic objective of the ReWaCEM project and share the consortium. I will then go through the different demonstration cases we had a look at during the project. I will select one and give a bit more detailed insight into one of them, and then summarize some outcome. So going quickly over the consortium, we had 6 R&D institutes doing the research and the evaluation, and each of the institutes were linked to one of the showcases or one of the core technologies. Then there were 4 SMEs developing the core technologies, and 4 industry partners actually hosting the application of the showcases in their industrial sites. The overall objective of the project is to reduce the freshwater demand in the metal processing industry, to also reduce the demand of makeup acids which are consumed in large quantities in these industries, to reduce the amount of disposed water, and to reduce the amount of disposed valuable metals that are disposed within these water streams, by actually applying membrane separation technologies as diffusion dialysis, membrane distillation, and advanced filtration. Going through the different showcase scenarios we demonstrated within the project. The first one was the recovery of hypochlorite acid and iron from a hot dip galvanization plant in Italy, in southern Italy, in Sicily, at the company Tecnozinco, and this plant was commissioned in March 2019. The second showcase was the recovery of sulfuric acid and copper from electroplating pickling solutions in electroplating plant in northern Spain, in Gijón, from Electronical, and this plant was commissioned in April 2019. The third case is the recovery of mixed acid containing fluoric acid and nitric acid from pickling solutions from stainless steel wire rod production in Germany, in Hagen, at the company Deutsche Edelstahlwerke, and this plant was commissioned in February 2019. And the last case is addressing a bit a different type of industry here. It's the printed circuit board production, and the the gold in the gold plating processes applied to plate the specific parts of the printed circuit board. There is a quite high value in these waters, so the recovery of and optimization of the rinsing steps is very crucial here, and this was demonstrated at ATNS in Austria and Fehring, and this plant was commissioned in March 2019. I will, because all of these cases are, let's say, linked in one way, but address a bit different issues. So I wanted to give a bit more insight into one, and I selected the hot galvanizing plant in Italy as the one I wanted to give some more information. To give some information about the pickling process itself, which is applied, the pickling is a surface pre-treatment step, basically, by reactive chemical etching to remove oxide layers and form some kind of surface texture on the metal pieces. So in this plant or in the hot dip galvanizing, there is different process steps, typically starting with a degreasing step, then the pickling itself to remove these layers, then the leftover of the pickling solution is rinsed in rinsing baths, then the pieces are dried and preheated, and then the galvanizing itself, so the coating step happens, which is then the core process, and then the pieces are getting cooled down and passing a quality control. And very similar type of process chains are also applied in electrogalvanization in stainless steel production. That's why this also showcase is selected in the project to show the variety of the application of the technology. But it's also applied in for example, silicon wafer production. The pickling bath, there's one problem basically. The acids are obviously consumed by the pickling process, and this consumption leads to the fact that the reaction products and particles are expelled into the bath. So there is a continuous or batch-wise recovery of this bath is necessary. And if we dispose these parts of the bath in these disposed solutions, there is still a lot of free acid next to the reaction products we need to dump somehow or treat. So there's a quite high economic and ecologic motivation to recycle these spent liquors to reduce the demand of makeup and to reduce the disposal quantities, and also to intensify the process, so we can then have a quite nice way to control these pickling processes and the qualities in the bath, which can then lead to process intensification. To give a bit an idea of the process we applied here in this hot dip galvanization plant, the approach was a zero liquid discharge approach to including recycling of acids and metals. So we start from here. This is basically the core process, the core pickling process. And here we have the waste stream that needs to be at least frequently disposed. And instead of disposing the stream, we feed it to the recovery plant, the ReWaCEM plant, as first into a diffusion dialysis membrane stack, which is operated with water as a draw solution, and the membrane itself lets pass the free acid, but has a retention to the metal salts. So basically the free acid passes to the second side of the membrane and is then fed to a second membrane process, which is a membrane distillation process driven by a waste heat from the plant. And in this membrane distillation process, we extract some of the water from the acid stream, from the clean acid stream, to push the concentration to the one we need to directly feed it back to the bath. And on the other hand, here we have metal-rich wastewater, which is, there is not a lot of acid in it anymore, but all the metal salts, and these are then precipitated in a reactor and then separated by a filter press. And while the solid parts is sold on the market, the liquid fraction can be reused in the fluxing bath of the plant. So actually there is no disposed stream anymore. So it's three core technologies. It's the acid recovery done by the diffusion dialysis. I'm sorry here, this should be acid concentration and water recovery in the membrane distillation, and the metal recovery in the precipitator. So here we can see a picture where the demonstration plant arrived at the industrial site in Sicily. And again, here you can see a rough schematic of the hydraulic layout. We see here in the pickling tank, we have 100 grams per liter concentration of free acid and about 250 grams per liter of the iron chloride, which is the reaction product and can therefore be more or less considered as the consumed acid. And here in the diffusion dialysis membrane, which is 15 square meters in surface, the recovery worked quite well and recovered more than 80% of the free acid, and then concentrated it in a membrane distillation unit, which was a 6 square meter unit, by a 20 to 40%, by a concentration factor of 1.2 to 1.4. And metal-rich brine was then fed to the reactor, and almost a complete part of the metal salts could be precipitated here, and this actually worked quite well, and also in a industrial scale and automized mode. So I want to already summarize. Within the ReWaCEM project, 4 industrial scale demonstrators for waste acid, metal and rinsing water recovery were successfully designed and built. Here we can see a bigger picture of the technology. The capacities of the different demonstrators range from 10 to 100 liters per hour treatment. The diffusion dialysis membrane stack were between 10 and 70 square meters. The membrane distillation stacks between 7 and 25 square meters. In the reactor, this is actually this one here, this was about 20 liters. The results were rated by applying life cycle analysis and water footprint methods within the partners in Stuttgart contributed that, and showed positive ecologic impact on various impact categories. The diffusion dialysis itself, we observed very high recovery rates from 80 to 90% in all the different treated acid systems, so also in the sulfuric and the mixed acid case. As future challenge, it can be said that additional recovery of the consumed, so the chemically bound acid, is the next step, and like these days this is typically done by very huge thermal pyrolysis plants, which is only capable for very big plant and very huge capacities and gas fired, so that would be something for future developments. Then in the diffusion dialysis itself, we observed a slight metal passage, so also the minimization of this metal passage would be a future challenge. for my last slide here, talking about the membrane distillation, a new concept for hazardous media treatment was developed because let's say, application scale membrane distillation systems typically address more drinking water production or anorganic salt concentration, but not so much, let's say, fluoric acid treatment or something like that. The waste heat is and also should be applied to achieve economic feasibility, and the acid concentration and rinsing water recovery works fine, but we need to be aware that volatile acid compounds pass these porous membranes. So a future challenge is to optimize the concentration concept specifically for volatile acids. In the reactive precipitation part of the technology, the process control worked very well, and we could recover a very high amount of these metal salts and achieve very good purities here. This was it from my side, and I thank you for listening.
Thank you very much, Daniel, for this interesting presentation and giving us some insight about the project. I have here two questions in the chat. The first is, how much does the recovery of 1 cubic meter spent hydrochloric acid lost in total, and how does it compare to prices for fresh acid and acid disposal?
Yeah, I'm sorry. Can you repeat once more?
Can you read it as well in the chat? How much does the recovery of 1 cubic meter spent HCl cost in total, and how does it compare to prices for fresh acid and acid disposal?
Yeah, this is a question that can unfortunately not easily be answered, because the main problem in this case was the fact that this production site in Sicily has first of all a lot higher prices for the acids than let's say typical mid-European prices, because the paths are very far. The second thing is that the disposal here is very expensive. So in that case, the disposed water streams need to be filled in trucks and then carried on the street up to Milano for treatment. So actually it's more addressing the disposal costs than the purchasing costs. I actually cannot say a price for the treatment.
Well, that's fine. Okay. Do you consider the metal passage as an important or large challenge? Small amounts might not be a problem, as I could.
Yeah, let's say the good thing here is that I think basically in all membrane processes we have to face the fact of rejection rates, and that they are not ideal. And here the nice thing is that we can tolerate some, because the product is not something someone wants to drink, for example. So it's we anyway feed it back to the pickling bath, where it's a lot higher quantity of this kind of salts or something like that. But it's clear that the goal is to get rid of the salt. So depending on the rejection of the metal salts, the size of the membrane stack to treat the whole capacity would change. So it's always a way to optimize the costs for the technology, if we can optimize the rejection.
Okay, thank you. And one last question from Anastasios Karabellas. What kind of MD membranes were used with acids for the membrane distillation?
Yeah, the MD membranes are naturally hydrophobic polymer membranes with very high porosity, And the membranes used here is PTFE membranes that are stretched and applied or laminated to a support layer. And this is actually very similar membranes, also known from various studies in saltwater treatment from many researchers. So it's a standard microfiltration membrane from PTFE used in the application of membrane distillation, and the average or nominal pore size was about 0.2 micron.
Okay, thank you very much. One last question from my side. I always like to know something about the impact and the bigger numbers. Can you tell us something about what you achieved regarding reduction of freshwater demand, reduction of wastewaters, and also reduction of residues or metals, acids? So the big numbers.
Yeah. So also this is something very difficult to wrap up. But for example, in this example, in the hot dip galvanization plant, actually we reduced this specific stream by 100% because we could recycle all the streams and reuse all the streams. But yeah, so in that case, this was very good. But the goal here was also to stabilize the quality of the bath to a certain level. So typically the baths are used for the pickling and kind of getting exhausted and more exhausted. So they are at the beginning, they're very high performance, and then they're used, and they get very, very low in performance, so that they don't lose too much acid while disposing. And by applying this technology, they can run the plant at a very high performance rate in the bath, and so mainly increase the productivity by about 20% of the whole plant. Yeah, so it's always questions. And also here, what is the reference? Do we consider just the disposal stream as the reference, and then we can achieve a very high a reduction, or is it that the demand of the whole plant, which it's always the problem for the LCA guys, and also to state the results correctly. I would like to, specifically for this question, to refer to our project leaflet. We have a final project leaflet giving some economic numbers and also the key results of this LCA models, calculations for all the 4 different scenarios. So maybe I can share this leaflet in this conference somehow.
Sure. I mean, you could, in the open chat, can we download it from your website, or if this is possible, just type in the website and everyone can.
Yeah, I will check and then give a link or something.
Mm-hmm. Yeah, that would be great.
Okay, thank you.